Solutions for perfect problem 1 for Math 111. Basic idea here is we're going to kind of pretend that you could fold a piece of paper 100 times. Can't actually do that after you do like, I don't know, 7 or 8 or something. You won't be able to do it. But if the paper is bigger, you could fold it more times. So kind of in theory, you can sort of pretend that you could fold it 100 times. At any rate, we're going to pretend we could fold it 100 times and then do some math, take advantage of some exponent rules to figure out how thick that paper would be. So in step 0, I kind of have you take a guess. I mean, there's no wrong answer, just a guess, because, I don't know, my guess would have been way off if I didn't already know the answer. And then step 1, really, you start with calculations. So in step 1, it says express the thickness of the paper in millimeters in the form 0.1 times a to the b power. So it says that our paper starts out as 0.1 millimeters thick, but then each time we fold the paper in half, it doubles. Right? You fold it in half once, it's whatever 0.1 times 2 is, 0.2 I guess. Then you fold it in half again and it doubles again, so now it's 0.1 times 2 times 2, or 0.4. You do it again and again and again and again, and you keep multiplying by 2. So what would you get if you folded it in half 100 times? I guess you'd get 0.1 times 100 of these 2's. And instead of writing times 2 times 2 times 2 times 2 and so on, you can just write 0.1 times 2 to the 100th power. So this is the quantity that we're going to be working with. I guess millimeters if we're going to be careful about units. But this doesn't really have any meaning, right? I mean, you can see that this is the answer maybe, but how far is that? I don't know. Well, let's figure it out. So the way you figure it out is by kind of going through the rest of the steps. Step 2 says, using your exponent rules, rewrite your answer, rewrite your answer from step 1 in the form 0.1, okay, times a raised up to the 10th power raised up to the c power. Okay, it's a little bit tricky. Still going to be in millimeters. So what they're saying is you currently have 2 to the 100th power. A was equal to 2. You no longer want to have 2 to the 100th power. You want to instead have 2 to the 10th power. But 2 to the 100th power is not the same as 2 to the 10th power, so you have to raise it to some other exponent c. And this is where you have to know the exponent rule, that if you're raising an exponent to another exponent like this, you multiply these two numbers together. So because 10 times 10 is 100, I can rewrite as 2 to the 100th power as 2 to the 10th power to the 10th power. Doesn't really help any. This isn't any more clear than this was, but it's another equivalent form of this. Let's go on. Step 3. Although 2 to the 10th power is equal to 1024, to make the calculations easier, we're going to assume that 2 to the 10th power is 1,000. It's close. It's not really 1,000, it's 1,024, but pretend it's 1,000. The reason you might pretend it's 1,000 is because what I have in the parentheses here is 2 to the 10th power. And if I just pretended that 2 to the 10th power was 1,000, then what I could do is I could rewrite it as 10 to some other power, because 10 to some power is equal to 1,000. What power do you have to raise 10 to get to 1,000? Well, 10 times 10 is 100, and 10 times 10 times 10 is 1,000, so I guess 10 to the third power will be equal to 1,000. So what I'm doing is I'm saying 2 to the 10th power is really 1024, but pretend it's 1,000. Why pretend it's 1,000? Because 1,000 is 10 to the third power. It'll end up that it's helpful to have 10 as our base. Number 4 says use some exponent rules to rewrite your answer as 0.1, okay, times 10 to some power. So the question is 10 to the third to the 10th, what's that equal to? Well, the answer is that's 10 to the 30th power, as we already talked about. We have this exponent rule that says when you raise an exponent to another exponent, you just multiply those two exponents. We got 10 to the 30th power. So 0.1 times 10 to the 30th power. We're still in millimeters. So for step 4, that's this form. But in step 4, it says, wait, then you're not done. Rewrite that as just 10 raised up to some power. So 0.1 times 10 to the 30th, turns out that's 10 to the 29th. How did I get that? Well, 0.1 is the same as 1/10. So really, you're taking this number and dividing by 10. I guess that's one way to think about it. Or when you multiply by 0.1, you move the decimal spot one place to the left. You get 10 to the 29th. So what we got is that our answer is 10 to the 29th millimeters. That's good. That's better. Still something hard to picture in your head. But since we have base 10, we'll be able to, in step 5, express that quantity in maybe a more meaningful way. It says your answer, 10 to the 29th, is in millimeters. Convert it to meters. Well, let's see, there's 1,000 millimeters in every meter. So if we have 10 to the 29th millimeters, I don't know why I wrote that so high, 10 to the 29th millimeters, and we wanted to convert that into meters, what we would do is we'd multiply by the conversion factor. We would say that for every 1 meter, there's 1,000 millimeters. The way a lot of people remember this is you can kind of cancel out these units in a sense. This one's up top, this one's down on the bottom. So what's 10 to the 29th divided by 1,000? Well, it's 10 to the 26th. So, okay, our answer is 10 to the 26th meters. Still doesn't really have a whole lot of meaning. So let's convert it into kilometers. Same idea. 1 kilometer is the same as 1,000 meters. Metric system works out nicely. So 10 to the 26th divided by 1,000 will give me 10 to the 23rd kilometers. Starting to see that this is a really, really large answer, 10 to the 23rd kilometers. How big is it? Well, step 6 says kind of Google this, look it up. Well, let's see. I kind of already did it. Let's first convert into light years. So 10 to the 26th power kilometers, maybe in light years, and see what Google tells me. Google says that 10 to the 26 kilometers is the same as 10 to the 13th light years. Wow, it's a lot of light years. This is approximately equal to 10 to the 13th power light years. Did I write the right thing in here? Oh, I was supposed to do 10 to the 23rd. 10 to the 23rd kilometers is 10 to the 10th power light years, roughly speaking. Oh wait, 10 to the 10th power, that's a 1 with 10 zeros after it. What we're saying is that our stack of paper would be 10 million light years tall. 10 million light years tall. No, we're not. That's not 10 zeros. That's 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're saying it would be 10 billion light years. It's pretty big, 10 billion light years. That's ridiculously big. That's bigger than you can even fathom. How far is that? Way further than the moon, way further than the sun. 10 billion light years? This is what I did. I said, how big, Google, is the universe? Tells me the observable universe is 13.8 billion years, is billion light years. The universe is 13.8 billion light years. I guess that would be the radius of the universe. That's ridiculous. This is almost as big as the radius of the universe. Not the solar system, not our galaxy, nothing like the universe. It's ridiculous. The point of this whole thing is just exponents get large really quick. 2 is a relatively small number. Raised up to the 100th power, I mean, I guess 100 is big, but it's not huge. 2 to the 100th power, that many tenths of millimeters. I mean, if you had that many pieces of paper and stacked them all up, I mean, you couldn't do it. It would be 10 billion light years tall. Crazy. So ends this problem.